acceleration here. And it says, what is the quadratic fit term A? Well, for this 1 degree, that happens to be 0.0628. 0.0628. And what we're going to do is we're going to spend some time with doing some calculations. We're going to use our equation for motion, and we're going to convert this A term from the quadratic fit into acceleration. What does it tell us from this moving? Okay. Now, down here, when we have velocity versus time, we're going to try to fit this to a linear fit. Again, it's going to look kind of goofy because the data is so weird. Let's give this guy a shot. We're going to fit this to a linear fit. And again, the data is really low down here, but it's really high up there. Because we're averaging it, this might be the power of averaging. We're going to see how this works. Okay, so the linear slope term is, if I read that properly, the slope is 0.136. 0.136. So we have two numbers that we got from our experiment. 0.628, which was the A term of this fit, and 0.136, which is the slope term of this fit. Okay, those two numbers, and I think I've written them down properly. We're going to calculate the experimental acceleration, and we're going to calculate the experimental acceleration velocity, and then we're also going to calculate the expected value from this diagram based on this tilt angle, which we measured over here. What does our theory suggest how fast this should be accelerating if this happens to be the acceleration due to gravity, and now we have this small component being with track? That's the experiment. That's not too bad. We just need to do the experiment 2 more times at 2 different tilt angles. Now, the reason why we're going to do 2 different tilt angles is perhaps if we go ahead and tilt the track even more, perhaps this goofiness with our cart not behaving as it should, maybe that will help that to sort of behave a little better because it's moving a little faster, giving it a bigger shove. So I know what the procedure is now. I'm going to close that. I'm going to go ahead and I have my data, so I'm going to go ahead and experiment and delete all runs, or last data run, that's fine. Yep, and there they go. Now I have the fits still there, so I'm going to go ahead and get rid of that fit. I'm going to turn off the linear fit down there, and then I'm going to turn off the quadratic fit up there. I'm sorry, I turned it back on because I'm an idiot. There's quadratic. I'm going to select this again and then turn off that fit. There we go. Now I turn them back off again because I don't know where this guy's going to be. And then what I want to do is I want to increase this tilt. And to help me, I brought along some boxes. Yay. Random boxes with some random electronic parts in it. I got it back from the stock room. I'm going to go ahead and take this and put this up on top of here to make this a little bit larger. Okay, so now I should have a larger tilt, and if I look at this guy even closer, let me see what I got down here. I'm seeing that that is about, if I stop talking, I'm seeing about 2.5 degrees. So if this is 0 and that's 5, it's sort of in the middle, maybe 2.5, 3 degrees, maybe. I know this guy's, I'm talking, so I'm going to try to stop it. There we go. Yeah, I'm going to go ahead and say 2.5 degrees. It's halfway between the 0 and the 5. So 2.5 degrees for this guy. So 2.5 degrees. That's fabulous. So now I have a larger angle, which gives me a larger component of the acceleration in this direction. So I'm hoping this thing will go much faster. Before I even take any data, I'm going to check it out first. Maybe this guy, I want to see if it crashes or not. Here we go. Oh yeah, that's going much faster. I get a much bigger bounce. It's as if I'm throwing it much higher into the air. I'm getting lots of bounces, so maybe we'll get quote-unquote prettier data. I don't know if the data will be better, but at least it's prettier. I don't know if pretty helps things out, but let's give this a shot. So I'm going to move this guy up here. I'm going to go ahead and have this guy be at 30, and I'm going to click on the start, and then I'm going to grab the rail so it doesn't kick out down at the bottom. So here we go. So I'm going to go ahead and press start. Let it go. This is a nice bounce. I like that a lot. And we're done. I can go ahead and stop this. Now let's look at the data. Wow, again, if I was just looking at beauty, I think this first bounce from here to there now looks a little bit better, like a proper parabola. It doesn't look as squished. And my velocity down here doesn't look as squished. You can still see I have some data down here that was selected from before. So let me click on this data and not select it. There we go. So I'm still looking at this center bounce here. This bounce happened a little bit earlier because it was moving faster. If you recall from our experiment before, when we had this thing just rolling with the fan, this is what the data looked like. It started at a certain position. This is 0.3. There's 0.2, there's 0.4, there's 0.3. It's telling us what's going on. And then it just sort of takes off like a parabola. That looks pretty well. This was the data we took the first time we used this data. And this looks like our velocity. It sort of starts at 0 and then it goes down. But this time we're allowing it to bounce. So instead of grabbing this data, which we did for the first experiment, for this experiment, we're grabbing the bounce data. And it sort of looks like an entire parabola. I'm anxious to see how well that fits. So I'm going to go ahead and grab this guy, just grabbing the data in the first bounce parabola, which is this guy. And I'm going to go ahead and fit it using the quadratic again. The mean squared error is actually about the same, e to the minus 4, surprisingly, as far as things canceling out. But at least to my eye, it looks like it fits a little more nicely. It looks like the red fit is fitting those data pretty cool. Let's check out the A term we get from there. The A term this time around at 2.5 degrees is 0.197. 0.197. And of course, we don't know exactly, without doing the math, what that means about the acceleration, but we can see that this A term, however the relationship is, it's larger. In fact, it was 0.06. You can just think of it being 6, and now it's 19. It's almost 3 times as larger. So I don't know if that's true or not, if that scales right with the acceleration, but I would guess that looking at this data and looking at our actual experiment, the acceleration was bigger this time because we're now getting closer to being vertical. We're not anywhere close to being vertical. We're only at 2.5 degrees, not 90, but not too bad. How about how this data looks with the velocity down here? If I select this data and get this stuff in the middle and then go up here to fit and grab a linear fit, okay? Again, it's not perfect. The mean squared error is 0.002. This is a little low there. It's a little high there. Something's happening in the middle. That's fine. But we want this data. The data is 0.398. 0.398 for the velocity. I'm sorry, I said for the velocity fit. The slope of the velocity curve happens to be 0.398. And we're going to calculate what that means in acceleration. And then we have one more of these guys to go. So it worked so well the first time. Let's grab a second box of electronic doodads and move this guy out of the way and see if I can get this guy to go inside there. Fantastic. It's ready to roll. I'm actually leaning against the table down here, the edge of the table. I'm not even using these legs anymore. I could move the legs down if I want, but this is fine. Let's see if this works. Let's see if it crashes and burns anything first before we take the data. I'm going to hold on to it, and let's see how this works. Well, that's fantastic. That's that's super fast, okay? We are getting more of the acceleration because we're tilting it towards the vertical acceleration. We're getting a larger component. So let this guy stop and stop bouncing around so that perhaps we can measure, get a good measure of the tilt, okay? So if I look at this guy, remember that was 0 right there. I just touched it. Of course I just touched it. Slow down. There's 0. There's 5. It's like a thread. I guess that's the term. It's a thread's width. It's a thread's width before 5. So I don't know. I'm just guessing. How about 4.75? I'm just making that up. That's a lot of sig figs. I've made up the 7 and the 5. I'm not sure. So maybe 4.8 to 2 sig figs? I don't know. We'll see what happens. Cool. I know it's larger, and because the angle is larger, our horizontal rail is now larger in the direction of down, which means that there's a greater component of acceleration, and this thing should move more quickly, and that's definitely what's happening. Let's clear our data. I select this guy down here. It's selected because of the yellow right there. I go ahead and clear the linear fit. I select this guy. It's selected up here. Clear the quadratic fit. I'm going to click somewhere and clear the selection. I'm going to click somewhere, select first, and then click somewhere, everything, and then I'm going to go ahead and delete it. So delete the last data run. Yep. We're good. Okay, we're all cleared up again. We're ready to go for run number 3, trial number 3. And the only difference between trial number 3 and trial number 2 is we've increased the tilt angle from 2.5 to, this is me being goofy, 4.75. I don't know, 4.8. Let's see what we get. Okay, so I'm going to put my data back here. I'm going to go grab my cart. Cart runs up there. Fantastic. We're going to start at 30 again. There's 30. And I'm going to press the start button and then move my hands, and so that I can watch it go down to the end there. Here we go. With this guy. That's pretty fast. Okay, that's a real nice toss. It's already bounced once. I only want the first bounce, so I'll go ahead and stop this. Okay, and I'll stop this guy from bouncing because it's going to take a while to bounce. Okay, the more acceleration I had in the direction of the rail, then the stronger the collision with the spring. The stronger the collision with the spring, the faster or the higher it flew it back up, and that created a bigger bounce. And that's why I created so many of them. So again, if this is not a very bouncy object, if I were to let it fall, it would crash and bounce off the floor. So that's not a good measurement. And again, but the ping pong ball, because it is a bouncy object, if I were to let it bounce off of the floor, okay, it'll do that a few times, and you can see, again, it's making little tiny parabolas as it's bouncing down. Because the floor and acceleration is down, the bounciness is up. Because this direction is away and this direction is negative or back, it looks like our data is negative, because this guy up here is our 1.9 meters where the quote-unquote spring is, or the floor is. So we literally are bouncing the cart off of that spring each time, and we're getting this bounce. This bounce is not across the floor or across the rail. The bounce is across time, okay? So here's our first bounce. Again, here is the flying down the cart, which was what we did the last experiment. Here's the first bounce off of the spring. Here's the second bounce. There's the third bounce. We're only worried about the first bounce. This time around, here is the first acceleration, a nice straight line. The first bounce acceleration is much straighter. It looks like this experiment is getting better and better data-wise, because whenever we move faster, then the little tiny idiosyncrasies of this thing not having enough lubricant on it. I probably should get some lubricant on here to make these wheels a little bit faster. Maybe we'd get some better data. So let's grab this data before we lose electricity on this Windows program. I need the quadratic fit term A for acceleration. So up here is the position. I want to collect just the data inside this first bounce. That's kind of cool. I go to fit, I grab quadratic, there's our fit. I think, I didn't record it, but I think our mean squared error, I can look in the video, was a 3e minus 4. Now it's a 2e minus 4, so it looks like our error is getting better. It's getting lower, just like the first experiment where the 0 is best. But this time around, the A term is 0.317. 0.317. 0.317. Okay. So it turns out that this guy is growing, it's getting larger. So again, we're not sure, we haven't done the math yet to find out what this is telling us about acceleration, but it's definitely getting larger. We saw it before. And then down here, we want to do the same thing. We only want to take the data inside the bounce for the velocity, which looks like that guy, and we want to fit it to a linear fit Again, I think the mean square error is better this time, and the slope is 0.639. 0.639. Fantastic. So these are the 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces of data, even though we did all this experiment, and this is all data as well. It's just that the things that we wanted from this experiment were just these 9 values. We wanted tilt angle, the quadratic fit term A, which is this guy, and the linear slope term M for this guy, and that's all we need in order to do our experiment and find out how well our prediction of this tilt angle here allows us to calculate what the acceleration should be along the direction of the track. Again, along the direction of the floor, or along the direction of the vertical, we know that the acceleration is what we typically have around Philadelphia, 9.8 meters per second squared, but we're looking to see what this component is. And it looks as if, angle-wise, the higher the tilt, the more we get closer to 9.8. That sort of makes sense, because if we tilt the whole way up to 90 degrees, like what would be against that wall over there, then our little tiny cart would fall as fast as the ping pong ball. It would accelerate as fast as that. All right, so for this, we're good. These are the 9 pieces of data that we needed from our data station and our individual setup. Okay, and thankfully, again, this company Pasco makes all these parts so that we can get this data on top of our in the laboratory. We're going to take these C6. We're going to take these 9 values. We're going to go back to the desk in a little bit in the future here, and we're going to calculate things out and see how well, after we calculate it, see how well these things compare. And again, that's going to allow us to do and look at a percent error. We're going to be able to see what that, it's not the mean square error, it's called the percent error, but it allows us to compare how well these 3 things are telling us the same answer. This is what our equations tell us, even if we didn't do the experiment, and this is what the experiment is doing. The experiment looking at just position as time tells us this. The experiment looking at velocity versus time tells us this. And then the calculation based on this graph over here and using all of our equations in physics will tell us another value, and we can see how close they are. Maybe they're fantastic, maybe they're goofy. If they're goofy in real